Alright, time for another draft science video presentation. Alright, start off with just the slight statement that Google is evil for so many reasons, blah blah blah. But we won't go into the details here, as we're just doing physics here. Anyway, so gravity's the subject. Probably should do some contextual history. This comes down to certain assumptions you make. You're sitting there saying, looking at the world, and you say, why do things fall on the earth towards the center of the earth? Why does it have this appearance? Then they figured out that the moon is orbiting the earth, and it's sort of being held in some kind of force that's pushing it, keeping it from just flying away. And it does. This argument is basically just an argument about, well, push does seem like the right answer. Pull is a complex thing in our real world. You can understand most of your pulls, or all of them, frankly, really amount to pushes from someplace else. If you remove pressure, the external pressure pushes something into the absence of pressure. And although I haven't seen a whole lot of writing on that kind of a subject 300 years ago, I'm pretty sure they were aware of these concepts. And so there would be a preference, I would think, towards looking for pushes. So 300 plus years ago, the idea of ultramundane particles that were constantly active in the universe, that the idea would be is that they would push on everything and push everything together if they in some way absorbed some portion of the energy. So if the rain could penetrate you and hit you and move you, you would absorb the rain, and the rain wouldn't fall on the things below you, kind of thing, and you would be pushed. And that was it was simple. It created the inverse square law, so it explained, much like photons radiating from a light bulb, it was just basically the opposite. If you put one object in a universe full of raindrops moving in all directions, it would appear from the position of the thing in the universe that the universe was pushing on it from all directions. That it was heading right for it, that it was personal, kind of a thing. So anyway, it's now called mock gravity. The first guy was Fadio, and then a guy named Lesage took Fadio's notes and republished, arguing for particle gravity. And then it died, in the 1700s, and nobody with any kind of respectability resurrected the theory. It had one major thing against it, which was that it creates drag. That is, anything you give velocity to in space would run out of velocity as it runs into more force. And so it would be dragged to a halt. So there wouldn't be any idea that I could throw a wrench to Mars. And it's a fact. I can throw a wrench, literally. I can just go into space with the space shuttle, and I can throw a wrench, and it'll land on Mars. And so that can't be explained with something that occurred to anyone else anyway. But like I said, it has huge advantages as a theory in that it's a real force. It's relying on push, which is so much more sensible than a pull. And, it fits all of the geometry and the rest of it. It creates the right amount of gravity, and it's proportional to the mass and all of that stuff. So I would argue that people just didn't think about how to fix the drag problem. And so they just decided that we're just going to go with, especially in the 1900s, they decided this whatever bent space is. It's not, you can't even call it a pull theory, but you still have to account for the fact that that's pretty much what it is. There's no force involved, there's no mechanism, there's just this magical notion that somehow everything knows to move towards other things. That's about it. It doesn't really make any sense. You can't bend 3 dimensions. So even though it has just as real paradoxes or flaws, in the sense that it doesn't really account for anything. The idea of bending space in 3 dimensions makes no sense. I mean, playing little games with a tablecloth, and the idea, a stretched tablecloth, and the idea that a mass would bend the tablecloth, well, that's all fine and good, but it doesn't have anything to do with our reality, which is there's 3 dimensions, and you can't bend a tablecloth in 3 dimensions. You can't create anything that makes sense. So in my opinion, that's just as big an obstacle as the drag issue for the particle model. And it doesn't have any of the assets of the inverse square law and all the other rules that are created by Mach gravity, all the ones that are fit. So it has a major flaw, and yet physics we've decided this is the truth, even though it's kind of a nothing answer. It's kind of gremlin-y. It's kind of ghosty. The magical bent space, versus something that's understandable. So anyway, so the other problems are understanding equilibrium and different aspects of gravity that seem that it's created by a previous condition in some sense, but it has to be current in another sense, in the sense that gravity has to be constantly recreated. You can't just absorb it in a previous time and then say you have gravity forever. You still actively have to keep producing it. So these are the other subtle problems, and they are understood to be not real problems when you do some thinking about it. So the idea would be, the equilibrium issue would be, is that as something heats up, that is, as something would create gravity, let's say it was creating gravity, so stuff would go into it, it would absorb the energy of the stuff, and then a little bit less stuff would come out, and that would be the idea. Well, you can understand how that works in the beginning, in the sense that stuff goes in and nothing's in here yet. Okay, so it's going to absorb some energy, but once there's stuff in here, once it's reached its capacity to absorb the energy, so it's cold and it gets warm. Well, once it's warm, then it's going to be producing as much stuff going out as is going in, and so it's going to reach a kind of equilibrium with the world. And so the Earth is sort of at that state in a lot of respects. It just stays a certain temperature, generally speaking, so as much energy that goes in comes out somewhere. But the catch is that you can understand where that's not actually true, because we have this idea that there's this conservation law, and it's a good theory. It's a good place to start, that you can't destroy something, but the fact is maybe you can destroy a little bit of it. So the idea that I have come upon to explain how you can create this constant absorption of a little bit of energy is to understand things on a nuclear level, and that what's really making an electron move. So this is another part where physicists in the 1600s really couldn't do real physics, because they really didn't know about electrons and protons, and they didn't have any idea of what the elements of matter were, and so they couldn't really understand how it might be interacting. But we have the advantage of knowing some of this stuff, so we can kind of understand it. So the idea would be is if you had an electron in space, there's lots of ways to think about how it would move when it interacted with a force. So let's say there was a force, a little ultra-mundane, very small, quantized, that is, they're all the same. They're just little bits of momentum, and they're all over the universe, and they're all moving in directions. Now, I would argue that the photons that we interact with all the time are basically those forces. They're just in an order. That is, they're all going in the same direction, and they have a distance between them, a frequency of nothing. So there's nothing between them, empty space, blackboard. And but there is a very specific frequency, and so that's a form of this energy that we can detect, and we can tune to the frequency and detect energy that's at that frequency. But most of this energy is not at a frequency. It doesn't have, it's all randomized in terms of its positions and its order and its arrangement and its direction. So anyway, the basic interaction would be is that this quanta is what's causing matter to move. So that matter doesn't really move. Electrons don't have momentum engines or anything. They just do whatever the force tells them. So you have an atmosphere around an electron, just like the Earth in empty space. And the Earth will do whatever the energy around it tells it to do. And that's basically how the electron works. Now, you just have to figure out, well, what's the mechanism? When this little bit hits, moving the speed of light, what happens? And the idea would be is that, well, if it leaves at the speed of light, okay, in some direction, or it does, well, I shouldn't even suggest that yet, even though that's the solution. So let's just get rid of the other noise, just so we have make it as clear as possible. So you have a little bit that hits. Now the idea would be is what happens? How does this energy convert into motion by this object? And which way is the motion, and all these questions can be asked. Now the idea would be is that it hits, and then the little bit stops, and the big bit rolls, like cue balls or pool balls. So you've converted this energy into this, and spread it over this mass, and now this thing rolls, and this thing's dead. Well, that's not very conservational in the sense that we kind of know that this energy doesn't just die. If we say it just rolls, then, what's rolling, But yeah, so let's just say it does move in a direction, and that the energy is spread inside the object. And now when it hits something, you'll be getting that energy back, that momentum. I mean, that sort of works. I mean, it sort of makes sense. But the problem is that electrons and protons don't appear to have that capacity, where you can just keep hitting them with something, and they'll go faster and faster and faster and fly through space forever at a speed. There's no real evidence that electrons and protons can do that, that the elemental bits they in fact do get dragged to a halt. They move into more force, and that more force slows them down and eventually wears them out, takes away all their energy. Alright, so anyway, no point in going through the possibilities. I'll just give you the right answer. Okay, the right answer is that this force, whatever it is, this little bit of energy, momentum, the raindrops in space, hit and they actually stick to the object. That is, they're absorbed by it, you could just say. And while they're absorbed, so they were going the speed of light here, but while they're absorbed, they go something less than the speed of light. So we could just say half the speed of light. And, for however many they possess, kind of thing. So the speed of light has been decreased, essentially, okay, while it's occupying the matter. And so the matter bit moves at half the speed. And then it interacts with something else, and every time it interacts with something else, that is, another raindrop hits, and it doesn't matter from where, it could come down from here. Whenever another one hits, both of them reflect. That is, this one bounces off and this one bounces off, because it's a kinetic reaction. It's just purely kinetic. It's things that are really, really hard, and so there's no slowness to it, or there's no anything. It's just that it's just like as if the two things hit each other head on, and they just totally reflected. And so every interaction, even if it's an interaction this way, just results in the same thing, which is everything just bounces off the change. It resists change entirely, and so it just rejects everything. So the idea would be is that when another one hits, both of them leave, and this thing, the piece of matter, stops. So it was going, and then it stops, and then when another raindrop hits it from another direction, it sticks, and it goes in that direction, so it goes again, and then when another little bit hits, it stops, and then it goes somewhere else, and then it stops, and then it goes somewhere else, and it stops, and that's how it travels through space. And so you can sort of understand that any movement is a degrade in the force. So any movement by atoms, by the elemental bits, electrons and protons, results in a destruction of some of the energy. So the photon, the constituent of the photon, the element of the photon, a piece of the photon, the quanta of energy, hits an electron. And so it starts off going the speed of light, which means it would get to a certain location in a certain amount of time. And the fact is, it doesn't get there in that amount of time. It's, first it's reversed in its direction, but let's just say that's happening in every direction, so that's negated as a significant fact. But the fact is that it's been slowed down. So something that was moving the speed of light, that had a momentum, let's just say the mass of these little things is 1, and they have a momentum based on the speed of light, so it's the mass times the velocity. And the fact is their velocity changes while they're stuck on a piece of matter, and that means they have less energy while they're stuck on the matter, total energy, because time is going to tick, 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 and so an event is going to happen less often. So you could just sort of understand that all the interactions define the energy of the universe. How many interactions are you having, per second? And if I make it so all of these lines that are defining interaction at a certain time, if all of them are delayed, okay, because they had to push a piece of matter for a while before they got here, then you're going to end up with a universe that has fewer interactions in it than it would have if all of these other pieces of matter that were slowing all this force down didn't exist. If you take away all the other players, this player is going to be moving a lot more. It's going to be moving this way, and then he'll stop, and then move that way, and then he'll move this way, and then he'll move that way. He's going to be doing that jiggling a lot faster if there's nothing else in the universe to slow the force down. So if nothing slows a piece of force, I do have to fix that someday. So if there's nothing else in the universe to slow the force down, then there's going to be more interactions on this object. So in a sense, it's clear that there has been a loss of energy. So the fact is that everything in the universe is full of these, everything that we call a thing, like an Earth or a moon. Inside of it, the electrons and protons are in fact moving constantly. Constantly stopping and going, let's just say. So as they absorb, as little bits of energy hit them, okay, from different locations coming right for them, okay, they keep stopping, starting, stopping, going, stopping, going, stopping, going, stopping, going, stopping, and they might not get anywhere, but they're constantly moving, constantly changing their location, and they're constantly doing it at the rate at which this stuff is hitting them. So at any one moment, you could argue for any quanta of time, okay, they're absorbing a certain amount of energy all the time. They absorb it going this way, and then they absorb a piece going this way, and then they absorb some this way. And so every millionth or billionth of a second or trillionth of a second, they're in the process of degrading a piece of quanta, a piece of energy that was going to be here at time 1 is only going to be here, at whatever time in the future, 5 minutes from now. It would have been here, and instead it's only going to be, here. And instead it's only going to be here because it was dragging this matter around. And so it's constantly absorbing, every time an electron moves, it's absorbing somebody's energy. Energy that was going to hit somebody ain't going to hit somebody when it was supposed to. So it's taken a little bit of energy out of the universe by moving the matter. And so that's causing gravity. That's causing a net change in the environment. Okay, so where you have this expectation that whatever goes in comes back out, so energy is going in, movement's going in, speed of light is going in, momentum is going in, and the truth is less, okay, a little tiny bit less is coming out in all directions, you know, all the same directions that the force is coming in. A little tiny bit less is coming out because these electrons and protons are absorbing it. And so the more electrons you have, the more protons you have in a piece of space, the more energy they've absorbed just by jiggling, just by slowing the stuff going the speed of light, converting it, okay, into something going half the speed of light, and therefore taking energy out. So every electron and every neutron and proton, they're all absorbing a little tiny bit of energy by jiggling, by being jostled. And when you add that all up, it adds up to the Earth is actually absorbing a little bit more. It's getting hit by more energy than it's actually producing out, which means anything that sits here is going to notice, okay, that the space out here is pushing with a certain amount, and the space here is pushing with less, a little bit less, because some of it got wiped out by this object, and so it moves into the lower pressure. And so that's the nature of the attractive force of gravity. It actually does mean that energy can be destroyed in the sense of a little bit of the quanta, the photon, however you want to understand the quanta, the bits of energy. A little bit of its energy for a little period of time has been diminished, and it's not destroyed, it's just slowed down a little. Like again, something that was going the speed of light is reduced, and if you reduce its speed, you reduce its momentum. And so you've taken a little bit of momentum out of the universe by moving a big blob of matter that only moves where the force tells it to move. So this is another simple, basic elemental argument, and makes sense to me that matter doesn't have a will, it doesn't have any ideas. Electrons don't have a plan. They don't have anything. All they have is an environment they're in, and the environment either has high pressure on one side and low pressure on the other side, and it moves in the direction of the pressure. So every little extra bit, I could have a billion things hit it from this direction and a billion hit it from this direction, 1,000,001. Okay, and that one means that this thing is going to move over here. So, you know, so I don't think I'll do the drag argument in this video, but drag is solved by understanding sort of the charge argument, that there are two different ways that this matter can interact. It can change the dimension in which the energy is in. So another way to change the energy equation is to actually change the direction of the momentum. So something goes in going this way, and if you can for free make it go out this way, or make it go, you know, in the third dimension, you know, was going this way, and you just change what dimension it leaves in, that's a very powerful mechanism for overcoming something like drag. So anyway, that's probably enough of a video for gravity. So gravity is a real force. There's real forces in the universe, real things. You don't have to give it any properties beyond understanding it has the capacity to interact with matter. I could make the simple argument that this force stuff doesn't interact with force. I could just say that's the rule, or I could explain that even if it does interact, it interacts purely kinetically, which means if two force bits hit each other, they just reverse direction. And that would look exactly the same as if they missed each other. If they missed each other, one's going this way and one's going that way. If they hit each other, one's going that way, one's going that way, so it just doesn't make any difference. So the force can't do anything to the force that changes the universe. But if it hits matter, then it changes the universe. Then the universe changes because the matter changes its location and is now reflecting to a different universe, to other things. It's changing what you see. I mean, changing the position of something changes how you're going to be affected, whether you get hit on this side of your face by the light or you get hit by this on this side. It changes the environment everything else exists in. By moving one electron from here to here, I change what it reflects to the rest of the universe. And it is really to the rest of the universe. When you're reflecting light, when you see somebody, you're seeing their electrons, and you're seeing them in a position. Now, you can't see the detail, you can't see specific enough, but the fact is, if I change the position of the electrons, I change what's actually hitting you, and what electrons are in you are going to get hit, which ones in your eye are going to get hit. So everything's always move matter, then you change. The force is now going to interact differently than if it stayed in the position it was in. So, and by moving matter, you absorb a little bit of time, a little bit of velocity. Yeah, it's probably enough. So a simple answer solves the problem. It's mechanical, and as stated, I'll explain how drag is easily overcome also. So, enough of a video on that subject, and I can only hope you can understand. It's just force and matter. The force is really small, little quantized stuff. The matter is also small, quantized stuff, protons and electrons. The neutron is a proton and an electron. You don't need quarks, and you don't need all the other crap. It doesn't really do anything meaningful. Those are the elements you need. You just need bits of force, bits of matter, and interactions between them. And that's it. The universe is made of that. It's not made of this wooey time dimension stuff and, you know, entanglement and all that nonsense.